Going to wait to see if it's streaming. I think I'm gonna start with the Italian thing today. And I think I'm gonna spend around 5 hours. I'm gonna try to spend around 5 hours or 4 hours and a half, something like that. So take a break after 1 hour and a half and come back and spend up to 5 hours, and then I'm gonna play poker, I think, off stream. And I start with the Italian thing, I think. And I have around 7 or 5 different articles to review yet. So yeah, 1, 2, 3, 4, 5. So those are the ones left, and I already started writing the ones about data structures. And I used ChatGPT to find a bunch of data structures. And I didn't know that there were so many data structures out there. I was actually really surprised. But I guess a bunch of them are just variations. But I didn't know there were so many. So obviously I think I'm gonna do only the ones that are the main ones that people use all the time. And look at this. It's crazy. And most of them are variations of trees, so I'm probably not gonna do them because it's probably a waste of time. But I think I'm gonna still live here because it might be interesting to do them. Because I think most people probably won't know about them, so.
Fa.
Fa.
Does.
Fisso.
Fisso.
Set. Unchanging.
3.
3.
3.
Desiderare.
Desiderare.
Desire.
Aria.
Aria.
Air.
Bene.
Bene.
Well.
Anche.
Anche.
Also.
Giocare.
Giocare.
Play.
Piccolo.
Piccolo.
Small.
Fine.
Fine.
End.
Mettere.
Mettere.
Put.
Casa.
Casa.
Home.
Leggere.
Leggere.
Read.
Mano.
Mano.
Hand.
Portare.
Portare.
Carry.
Grande.
Grande.
Large.
Compitare.
Compitare.
Spell. Words.
Aggiungere.
Aggiungere.
Add.
Anche.
Anche.
Even. Also.
Terra.
Terra.
Land.
Qui.
Qui.
Here.
Devo.
Devo.
I must.
Grande.
Grande.
Big.
Alto.
Alto.
High. Tall.
Tale.
Tale.
Such.
Seguire.
Seguire.
Follow.
Atto.
Atto.
Enact.
Perché.
Perché.
Why.
Chiedere.
Chiedere.
Ask.
Maschi.
Maschi.
Men.
Cambiamento.
Cambiamento.
A change.
È andato.
È andato.
He, she went.
Luce.
Luce.
Light.
Tipo.
Tipo.
Kind of thing.
Spento.
Spento.
Turned off.
Bisogno.
Bisogno.
Need.
Casa.
Casa.
House.
Immagine.
Immagine.
Image.
Provare.
Provare.
Try.
Noi.
Noi.
Us.
Di nuovo.
Di nuovo.
Again.
Animale.
Animale.
Animal.
Punto.
Punto.
Point.
Madre.
Madre.
Mother.
Mondo.
Mondo.
World.
Vicino.
Vicino.
Near.
Costruire.
Costruire.
Build.
Se stesso.
Se stesso.
Himself.
Terra.
Terra.
Earth.
Padre.
Padre.
Father.
I'm gonna start with topological sorts. I think I already looked into this sometimes. So this is the one that I'm gonna review first. Yeah, I already reviewed this one. Pretty sure. So I'm gonna go faster, I think, through this. The reason why the text is different is because sometimes I forget to remove this thing, so I end up doing the wrong indentation there. It doesn't matter that much, because the div outside of the blog, the post, makes it have the same, roughly the same length every time. But if you get too small, then I think it changes there, so... I left the minimum vertex I was doing offstream for later because I think is one of the hardest ones. And then I also, these strongly connected components, I've watched videos and studied, but it's also hard to understand because the concept is really hard to understand. I think I'm gonna remove this one. Because I don't think it matters that much. Oh, I got it. So in degree 0 means that it's a node that only has arrows that come from it to other nodes, I think. think I understand how it works. It's not that hard. Just getting the ones with degree 0. Then it loops through the neighbors of that node, decreasing the counts based on the amount of edges it has. No, it makes the degree of the other one -1. The neighbors. And then if it reaches 0, it appends to the Arduino. So if all of the nodes are not there, is because there's an imbalance in the amounts of in and outs, which means that there is a cycle. I think intuitively I understand how it works. And the algorithm is not that hard to understand either. It's a lot easier than the other ones. So I think the reason for starting with the ones that have 0 in degree nodes is because those are the ones that are going to start the graph. So that makes a lot of sense. And then you want to go from those ones to the other ones. And then the point of doing this cycle here, this loop, is so that you find cycles. Okay. Yeah, I get it. So when it reaches 0, it means that it is the next node on the flow of the graph, I think. Let me just make sure that I understand these parts, because it can be confusing. This part of decreasing the value is decreasing the value of the neighbors by 1. Right, because it's popping down. I guess what happens if no neighbor reaches 0 though? That's gonna break the thing. That means that there is a cycle there. Yeah, I actually don't understand this part, I think. Because if all of them I started at 0, and then the ones that have 1 in degree or have in degree equals to 0 or appended here. It adds 1 to the neighbors of the main ones. That's what it's doing. So it starts off with the main ones. The other ones are gonna have in degree 1. Also, when you subtract, they are automatically 0. And that's why it traverses, it's like breadth first search. Because all of the ones have 1. But it's gonna be different than 1 if one of them has 0 already. Because it means that it was visited twice. So it exists twice on the neighbor. I think I understand. No. So if there is a cycle, the value is gonna be -1 or more. And if there isn't, it's gonna be 0 because all of the neighbors of the main nodes are initialized with 1. So when you decrease here, it becomes 0, and then they are appended to the queue. The traversal continues. So each one of them can only be visited one time. Otherwise, the neighbors of the main ones, otherwise it becomes -1, and then they are not gonna be added, I think. Which means that the top order is not going to contain all the nodes. I think this one I can close because it is correct, I think. And I'm not going to modify anything there because I think I already did on a previous time. I remember looking at that one, I think 1 or 2 times already, so. I think I also looked into this one already, and I looked into this one I looked at, studied it as well, and I think the ones that I didn't look into is this Tutte polynomial and the minimum vertex I looked into yesterday, but it's kind of complicated, so I think I'm gonna leave this one for last, and then I'm gonna check to see if this one is easy because then I'm gonna do this one before this one. I also want to think more about this stuff here, about the NP hards and polynomial time. And it is something more difficult to think about. About what it means for something to be visible in polynomial time. Many approximations algorithms have been developed to solve TSP. This one, I think I'm gonna remove, is not that relevant. And so I guess this is a heuristic. And you can choose which one you want. I think I get it. It's not that hard, similar to the other algorithms. And I think this function here can be any heuristic you want. Depends on the application, probably. Yeah, distant function. I think I'm gonna go to the next one. I'm gonna leave this one like this. So let me look at this one, I think. Polynomial, also known as Tutte matrix, is a powerful mathematical tool used in the study of the graphs and matroids. What the fuck is a matroid? Remove this thing here. I'm gonna search for these things here. I'm gonna watch this stuff while I eat something. When it's time to take a break. And it's gonna take me some time to understand this. So I'm gonna have to spend a lot of time. I think I already do understand the basics, but obviously I want to understand exactly how it works. And this is not really good as well, because it doesn't explain what x and y are. I guess they are the points, maybe in a Cartesian plane of the position of the node. We're not really sure. I think it's probably better to do strongly connected components before this. Because of this, I think they are related. I think these three are gonna be really hard. I'm gonna start with this one. And for this two, I'm gonna watch a bunch of videos, I think. I think I might stop streaming and then just watch the videos off stream. It's gonna take me a lot of time to study those ones, I think. It's kind of annoying because I don't really care about this right now, obviously. Just want to finish the articles. But obviously I'm gonna study, make sure that I understand how it works and then review. But it is a pain in the ass that I have to do that now. So I can keep going with the other articles. I think this is the kind of stuff that I'm gonna study more when I start making articles about artificial intelligence. Because I think they are related. And the stuff that is more related to, I think, linear algebra and mathematics. And this kind of stuff, it takes a lot of time and I have to study a lot and watch a bunch of videos. Because it's not... Like the other ones are kind of straightforward. As soon as you understand the problem, you can see if the algorithm is correct or not and the applications. But things that are more related to mathematics is more difficult for me because I start thinking about a bunch of things about related to philosophy and the nature of mathematics, and there's a bunch of other different things that are connected to each other. So by reading stuff about this, for example, about the dimensions thing, about the independence of the vector, I start thinking about eigenvectors and then the notion of special relativity and how that relates to artificial intelligence as well, and all of these different things. So it becomes a lot harder to reason about what this is exactly, especially because the way that these things are framed as well most of the time. It's difficult to know like if it makes sense or not and what's the point of the thing. Is more abstract, I think. And ideally I would be making videos or making articles about this only once I have a bunch of different other articles already, so I can spend more time thinking about these things that may not be very practical. I think I'll be right back. I think I'll do only the strongly connected components now. Then I'll stop streaming. And I think I'm gonna play poker tournaments, and while I play the tournaments, I watch the videos for the other two articles. And then maybe I'll review them today, or I'll review them tomorrow on stream. Because after watching all of the videos, it's gonna be easier to understand. I don't understand what a low link array is. Or initializing stack of the array, a low link array. I'm gonna watch videos about this.
Hi.
Hello guys, welcome back to Take Dose, and in this video we will see the tangents algorithm for the strongly connected components. So in this video I will show you how you can use the tangents algorithm in order to find all the strongly connected components in a graph. I will be also showing you the dry run as well as the code at the end of the video. So let us first look at some of the concepts which will be useful for this tangents algorithm. So the first concept is to know about 4 types of edges. So the first type of edge is a tree edge. And what is a tree edge? If there is an edge from u to v, then there will be a parent-child relationship, and if this holds true, then that will be a tree edge. You can see that all the red edges are tree edges. I hope this is self-explanatory. Now if you look at the forward edge, then if you have two vertices u and v, and the relationship is u is the ancestor and v is the descendant, in such a way that u and v are not having any parent-child relationship, so this will be a forward edge. You can see that the pink line is showing a forward edge. Just the reverse of the forward edge is a back edge. So in this case you can see that if you have a vertex u and v and that is having a relationship of descendant to ancestor edge, so that will be a back edge. And the fourth type of edge is a cross edge. So if you have two vertices u and v, then from u to v you will not be having any ancestor descendant relationship. In such a case, that edge will be a cross edge. You can see that from 5 to 4 there is a cross edge. Okay, so I hope you got these simple concepts. Now let us assume that we are having this graph having 4 nodes and there is one back edge. Okay, and let us say we are taking a timer. So whenever we make a DFS call, our timer will increase by 1 value. Okay, so we will be starting from this node 0. Now at node 0, what will be the time? Time will be 0. So this is our discovery time. So we will be taking a tuple having 2 values. The first value will be the discovery time and the second value will be a low value. So the low value will indicate node with lowest discovery time accessible from the current node, and discovery time will show the discovery time of a node. So discovery time of a node will never change while the low value can keep changing. Let me just explain this graph and then you will come to know what are these low and discovery values. So if we start at this node 0, then the time is 0, and so the discovery time of this node 0 is 0, and the node which is accessible having the lowest discovery time is also 0. Okay, so there is no back edge here. Now if we move to the next DFS call, that is from 0 will go to 1, our time will increment by 1 value, and at 1 our discovery time is 1. So we discovered this node 1 at time 1, and what will be the node which will be accessible having the lowest discovery time? Well, that will be equals to 1, because the nodes which are present below will be having higher discovery time and there is no back edge. Therefore the discovery time as well as the lowest discovery time accessible from this given node is also the same. Now let us make the next DFS call. So if we reach to this 2, our time will increment by 1 value. So this 2's discovery time was 2. Okay, and now what will be the lowest node accessible from this 2? We do not know the future node, so we will be giving 2 here. Now from this 2 we will make the DFS call to 3. So at 3 the discovery time will be 3 because time will also get incremented, and from 3 the node with the lowest discovery time is this 1, which is having the discovery time as 1. So we will write here 1. Okay, now we have made all the DFS calls, and so we will return back to this 2. And when we return back, what we will do is we will have to update the node having the lowest accessible time which is accessible from the given node, because from this given node while filling we just saw the immediate edges if there are any back edges. But in this case there was a future node which is 3 which is having a back edge, and that is pointing to node 1 which is having discovery time 1, and here the value is 2. So this should be updated to 1. Okay, so you can see that this low value is now changed for this node 2, but the discovery time is still the same. Now from 2 we will go back to 1. Now for this one we will again update this low value, and that will be equals to minimum of already present low value comma the low value from the future nodes, which is in this case 2. So low value is 1, so minimum of 1 comma 1 will be 1, so this will remain here. And similarly for this 0, the low value will be minimum of already present low value comma the low value of the future node, which is 1. Okay, and why are we taking this? I have already explained this. There might be a back edge which might be going to some previous node. Okay, so we do not know about this. Therefore we will have to always take the minimum from the future node as well for the low values. So on traversing this entire graph, you can understand that as soon as we hit a node which is not visited, we will assign its discovery time by using our timer. And once the discovery time has been assigned, it will never change, but the low value will keep changing. Okay, so as soon as we make the calls and come back, the low value can get updated. So this is one important concept for this tangents algorithm. Now let us look at an example how the discovery time and the lowest discovery node accessible can be filled. So in this case I will be taking this graph example. Here we are having 6 nodes. Let us assume that we will be starting from this node 0, and initially our time value will be 0. So we will be first making the left calls and then right calls for this DFS. So as soon as we start at 0, the discovery time will be 0 and the lowest discovery node accessible will also be 0. Now we will make the left call, which is 1. So while making the call we will also increment this timer. So at 1 the discovery time will be 1, so we have written 1 here, and the lowest discovery node accessible will also be 1 now because we do not know anything about future. So we will make the next call. While making the next call, increase the timer. We will be at 2. So at 2 the discovery time of 2 is 2 and the lowest discovery node accessible will also be 2. Okay, and now there are no outgoing edges, so we will go back to this one. We will backtrack. Now since we have reached to this one, we will explore the other outgoing edges. So from 1 there is an outgoing edge to 3. So we will go to 3, but we will also increment the timer. Now once we reach to this 3, the time is 3, therefore the discovery time of node 3 will be 3, and the lowest discovery node accessible till now is also 3.
Yes, that's the parts of the recursion here. This part here. Probably.
Now from 3 we will make DFS call to 4. So we will also increment the timer, and the discovery time of 4 is 4. And the lowest discovery node accessible from this 4 is also 4. Now we will explore this node 4. So from 4 there is an edge to 0. But you can see that this 0 is already having value 0. This means that this 0 was actually already discovered. And since we are going back to an already discovered node, so it means that this is a back edge. Okay. So in this case there can be 2 types of cases, like it can be a back edge or it can be a cross edge. So I will be explaining you in later half of the video how to differentiate between them. But in this case, you can see that this is just a back edge. So as soon as you find a back edge, this means that we are forming a cycle, and so this will also be contained in a strongly connected component. So we do not need to actually traverse to this 0, but instead of that, since we are having a back edge, so we will have to update the low value of this 4. So low value of this 4 will now be equal to minimum of already present low value, which is 4, comma the discovery time of this 0. So discovery time is 0. Now in this case, you can see that we are not taking the minimum of 4, comma the low value at 0, because low value at 0 will mean that there might be some multiple edges. So this I will explain you in the later half of the video. In this case, we will be taking minimum of 4, 0, which will be equal to 0. So now let us explore the other edge. So other edge is going from 4 to 5. So when we move to 5, our timer will also increase, and at 5 our time, that is discovery time is 5, and our lowest discovery node accessible will also be 5. Now there are no outgoing edges from 5, so we will backtrack to 4. Now at 4 we had explored each and every possible path, so we will backtrack to 3. Now at 3, we have also explored this path. So we will have to update the low values. So we will have to keep on updating the low values. So low at 3 will be equals to minimum of already present low value, that is minimum of low at 3, comma, that will be low at future node, which is 4, which I had already explained in this part. Okay. So low at 3 is actually 3, but low at 4 is 0. This indicates that if you go to 4, then there is a package from 4 which is going to 0. So your low value at 3 will get updated to 0. Okay. Now from 3 we will back to 1. So again we will have to update the low value at 1, which will be minimum of low value at 1, which is 1, comma, the low value at 3. So low value at 3 is already 0, and so this will be equals to 0. At 1 it will be 0. Okay. Now from 1 you will go back to 0. So at 0, your low value and also your discovery values are both the same. Therefore this is the head node of your strongly connected component. So I think this is giving you a rough idea of how to use this low time as well as your discovery time. So whenever your low value and discovery value for a node are both equal, then that node will be the head node of your strongly connected component. So in this case you can see that low and discovery are used to identify the packages. Let us now look at the next concept. Well, let us take this first graph. If edge is pointing to a visited node already in stack, then it's a package. So let us simply perform our DFS using a stack. So if we use a stack, then we will start at 0. We will go to 1, push this 1. We will go to 2, push this 2. Again we will backtrack to 1, then we will pop this 2. From 1 we will go to 3, push this 3. Now again backtrack to 1, so pop this 3. Again backtrack to 0, pop this 1. Okay. And now from 0 we will make a call to 4, so we will push 4. From 4 we will make a call to 5, push this 5. Okay. And now you can see that our stack is having 0, 4, 5, and from 5 there is an edge to 3. But this 3 is already visited. Therefore, if edge is pointing to a visited node already in the stack, then it's a package, otherwise it will be a cross edge. So in this case 3 is not present in our stack. Our stack is only having 0, 4, and 5. So this is not present in our stack, and therefore this will be a cross edge. 5 to 3 is a cross edge. If this 3 was present in our stack, then that would have been a package. Like in this case. In the second example, if we start from this node 0, then this 0 will be pushed. Okay. From 0 if you go to 1, 1 will be pushed. If you go to 2 will be pushed. If you go to 3, 3 will be pushed. And again from 3 we are going to 0. Now 0 is already present in stack, and therefore this will be considered as a package. So this is a technique in order to differentiate between a cross edge and a package. I hope you got this concept now. Okay. Now stack is required to keep track of the nodes present in the strongly connected component. And since we are using DFS, and since you also want to maintain the nodes which we have traversed for our component, so this is very logical data structure to use, which is a stack. Now let's look at the next concept. The next thing is why cross edge is not cross edge. Let us consider two strongly connected components, SCC1 and SCC2. So the edge which is connecting them both will be called as a cross edge. Now since SCC1 is a strongly connected component, we can visit all the nodes from every other node in this component, and the same goes for SCC2 as well. But between these two components, we cannot have path from each and every node to every other node, and therefore they are two different components. So if you want to find the strongly connected components, and we are, let's say, starting from this SCC2, and we have already visited this SCC1, there is no point in going from this SCC2 to SCC1 because they both are different components, and they will never be falling in the same component. Therefore, there is no point in going back. Now you might be thinking that there might be a package from SCC1 to SCC2. So if there was a package from SCC1 to SCC2, then you can traverse to each and every node in both the components. That is, all the nodes in both these components will be having path between each and every node. And so this SCC1 and SCC2 will together form a single strongly connected component. And since this is not true, since they are forming two different strongly connected components, so there will never be a cycle. Therefore, if strongly connected component is formed as a node, then the graph will always be a directed cyclic graph. So if it represents a cluster of node which is forming a strongly connected component into a single node, then the graph which will be formed will always be a directed cyclic graph. And the edge connecting both these components will be called as a cross edge. Therefore, there is no point in processing a cross edge. I hope you have understood this. If you didn't, then please repeat the video in order to understand it. Let us now look at the next concept. So the next concept is about low and discovery analysis. Let us start from this node 0. And let us also take time is equal to 0 initially. Okay. Now at 0, our time is 0, therefore the discovery time will be 0. And we will be taking the total of values. The first value will be the discovery time, second value will be the low value. Okay. Now the low value will initially be 0. Now we will make the DFS call to 1. So the time will increment by one value. So here we will be having 1, 1. Now from 1 we will be calling to this 2. So the time will increase and it will be 2, 2. Now from this 2 we will make a call to 5. Here the time will be 3, 3. Okay. And from 5 you can see that there is an edge to 0. But 0 is already discovered since it is having discovery value of 0. And since this 0 is already present in our DFS call stack, we started from 0. So this is present in our stack. Therefore this is a package and not a cross edge. So the discovery time of this 0 is 0. Therefore the lowest possible discovery time to which we can reach from this node 5 will not be 3 but it will be 0. Okay. And now when we go back in the DFS call, because our DFS call is done now since there is only one outgoing edge. Now if we go back to this 2, then the earliest possible discovery time node to which we can reach from this node 2 will be equals to 0 and not 2, because we can reach to this 0 having discovery time 0 via this 5, and the same goes for this one. This will also be 0. So this is how the low values for each and every node can keep changing. Now let us explore further. From 2 we will go to 3 and the time will increment to 4. So here we will write 4, 4. Now we will make a call to 4. So this will be 5, 5 because time will be 5, and again we will make a call to 6, time will be 6, and this will be 6, 6.
I don't like this explanation too much, to be honest.
Will be used in order to differentiate between a package and a cross edge. Okay. Now let us start processing and show how this algorithm works. Now let us start at this node 0. So at node 0 the time is 0. So the discovery time will be 0 and the load time will also be 0. Okay. And now we will increment our timer. So this will be 1. And since we have traversed this, so this will be pushed into the stack. So 0 will be pushed. And now since this is present in stack, we will make it true. Okay. Now all the steps are done. So we will make the next DFS call. This will be to 1. So now this 1 is not discovered. This is having value -1. So we will traverse it. It will be assigned value 1, which is the time value. Low will also be assigned to 1. Now the timer will be increased to 2. Now we will push 1 into the stack. And since 1 is present in stack, this will be made as true.
Like
Now,
this whole time I don't understand what's the point. What are you trying to achieve? I think it would be better to explain first. Like what is the thing? Like what is a strongly connected component? And clarify that rather than just go through the process of the algorithm, let's say. Because it feels very redundant, this explanation of these steps. More concerned about understanding the concept.
the time equals to 2. So this can be either a package or a cross edge. So how do we verify that? Now you can see that in stack value of 2 is equals to false. This means that this 2 is not present in our stack. You can see this was fogged off. Now since this 2 is not present in our stack, this edge will be a cross edge. So this is a cross edge. And I've already said that we will be ignoring all the cross edges between two strongly connected components. So we have already at V, since we are only allowed a single package. So this 6 will be ahead of the strongly connected component. So in this, and this will become false. Okay, 6 and 5 will not be false. So we will back to 4. Now we have traversed both outgoing edges from 4, which is to 0 and 5. So now this value, 3 and load time are both the same. This algorithm. This is a simple code for this algorithm. In this case, I have just made a similar graph, and after making the graph using adjacency list, I will be calling the find strongly connected components using Cardinal algorithm. So in this case, I have declared the discovery as well as the low vectors and assigned them values -1. I have also taken the array present in stack and assigned all the node values to false, since none of the nodes are initially present in the stack. Now if node V is not yet discovered, then we will be having value that was the head node, and we were actually popping the elements from stack, and then we were printing it. So once we reach to the head node of our strongly connected component, we will print the entire component, and after that we will just backtrack from that edge. So this is the entire algorithm, and I hope you were able to understand.
In this video, we are going to talk about another strongly connected component-related algorithm, the so-called Tarjan algorithm. Of course, the aim of the algorithm is the same as we have seen for Koszary algorithm. We would like to end up with strongly connected components. In order to understand Tarjan algorithm, we should consider forward edges, backward edges, and cross edges. So let's suppose that we have a graph like this with directed edges. A forward edge is something like this, a cross edge is something like this, and a backward edge is something like this. Okay, so there are 3 types of edges: backward edges, cross edges, and forward edges. So Tarjan algorithm runs in linear time. We use a depth first search again for traversing the graph, as we have seen for Koszary algorithm. But we have a very important fact, the so-called stack invariant. When depth first search recursively visits a node V and its descendants, those nodes are not necessarily popped from the
The problem I have with this is that the way that they frame the thing, that's what I don't understand. But I guess it's because it only works for directed graphs. But the way that I think, because this definition is not good enough for other types of graphs, the way that I think is like, imagine if you have a graph that is a square and all the nodes are connected. How are you going to define in that situation what's a backward edge or a cross edge or the other one? That because I'm thinking about the definition on all types of different graphs. So let's say here all the nodes are connected to each other. It would be far more difficult to understand like which one is which, and that's what I'm trying to capture in my mind to understand in the algorithm how it works. So when they explain here, it makes a lot of sense, obviously, because it's a super easy example. But if you extrapolate to all types of different graphs that you can have, then it becomes very confusing because how you think about the definition when you're coding the algorithm. Like what does it mean for the edge to be like that when all the nodes are connected?
Backward edges, cross edges, and forward edges. So Tarian algorithm runs in linear time. We use a depth first search again for traversing the graph, as we have seen for Kosharayu algorithm. But we have a very important fact, the so-called stack invariant. When depth first search recursively visits a node V and its descendants, those nodes are not necessarily popped from the stack when the recursive call returns.
Because a cross edge can be a forward edge as well. Like from one way of looking at it. But then I guess the difference would be like in the flow of the thing. Where the cross edge is going to be when you have a node that receives more of one edge. Maybe. That's what's hard to understand.
Three types. Node V and its descendants, those nodes are not necessarily popped from the stack when the recursive call returns. A node remains on the stack after it has been visited if there exists a path in the graph from this node to some node earlier on the given stack. So this is the stack invariant that sometimes nodes are not going to be popped from the stack when the recursive call returns. So at the end of the call that visits V, we know whether V itself has a path to any node earlier on the stack. If yes, which means that V has a path to any node earlier on the stack, the call returns and V stays on the stack. If no, so V doesn't have a path to any node earlier on the stack, then the V node must be the root of its strongly connected component. And basically every other item on the stack is the part of that given strongly connected component. By the way, Tarian algorithm is very, very hard to grasp as far as the theory is concerned. We are going to implement it together with lots of debug comments to the console, and I think it's going to be clear. Okay, so it's very important that for
I think that one requirement is that you have to implement with that first search. So you use a stack and then it becomes a tree structure because of the way that stacks are implemented recursively. So the algorithm is always going to have that. Is always going to transform the graph, whatever the graph is, into the tree structure because of the implementation of that first search in a recursive way. Where depth first search is recursive, so that actually you can have the depth first search through a loop, but I guess you always implement as a recursion, and then you create the definitions inside of the recursion based on the tree structure that is going to become the graph is going to become the tree structure because you're implementing depth first search, and then because of that you can create these different rules to see what type of edge it is, I think.
Tarian algorithm, we have two parameters, the index and the low link. In our implementation, we just have the low link because the index is the integer we assign to the nodes consecutively in the order they are visited by that first search. The low link is the smallest index of any node known to be reachable from node V. Okay, we are going to implement it, so I'm not going to talk about it. What's very important that if the low link is equal to the index, there is no backward edge to any other node, so the parent node is the root of a strongly connected component. If the low link is smaller than the index, it means that we have found a backward edge in the given graph. But as I said earlier, we are not going to use the index in our implementation. So for example, we have 7 vertices, 1, 2, 3, 4, 5, 6, and 7, and it is a directed graph as you can see. We start at a given vertex, for example, the vertex 1, and recursively we use depth first search to visit every neighbors of that given vertex. It has a single neighbor, the vertex 5, so we consider vertex 5, we consider every single neighbor for vertex 5, which is the vertex 2 basically, and the vertex 2 has a single neighbor, the vertex 1, but we have already visited the vertex 1, so we can come to the conclusion that this 2, 5, and 1 consists the first strongly connected component. Then we consider other vertices of the original graph, for example 6, and we recursively visit every single neighbor of that given vertex, then the neighbors of the neighbor of that given vertex, and so on. This is how depth first search works. It's going to go as deep into the graph as possible. So we visit recursively 3, then we visit recursively 4, and 4 doesn't have any unvisited neighbor because we have already visited 3. So it's going to be the part of another strongly connected component. 3 is the part of another strongly connected component. Okay, but as you can see, we are not able to reach any more unvisited vertices because we are not able to reach the 7. We are able to reach 2, but we have already considered 2. 2 has already been considered to be the part of the green strongly connected component. So we can come to the conclusion that the second strongly connected component contains only 2 vertices, 3 and 4. Then we have the 7 on the stack and the 6, and again we can come to the conclusion that they are part of a different strongly connected component. So there are 3 strongly connected components in this graph: 1, 2, 5, 3, and 4, 6, and 7. So we are able to find the components with the help of Tarian algorithm. We just have to define another parameter, the low link. This is what we are going to implement in the next video. Thanks for watching.
Hello and welcome back. My name is William. Today I want to talk about the fascinating topic of strongly connected components and how we can find them using Tarzan's algorithm. So what are SCCs, or strongly connected components? I like to think of them as self-contained cycles within a directed graph, where for every vertex in a given cycle, you can reach every other vertex in the same cycle. For example, in the graph below, there are 4 strongly connected components. I've outlined them here in different colors. If you inspect each SCC, you'll notice that each has its own self-contained cycle, and that for each component, there is no way to find a path that leaves a component and comes back. Because of this property, we can be sure that SCCs in a graph are unique. To understand Tarzan's algorithm, we're first going to need to understand the concept of a low-length value. Simply put, the low-length value of a particular node is the smallest node ID reachable from that node, including the ID of the node itself. For this to make sense, I'm going to label each of the nodes in our graph by doing a DFS. Suppose we start at the top left corner and label that node with an ID of 0. Now let's explore the rest of the graph and assign IDs to all our nodes. I will let the animation play and you try and follow along. Alright, now that we're done labeling the nodes, inspect the graph and try to determine the low-length value for each node. Again, the low-length value of a node is the smallest node ID reachable from that node, including itself. For example, the low-length value of node 1 is 0, since node 0 is the node with the lowest ID reachable from node 1. Similarly, the low-length value of node 3 is 2, since node 2 is the node with the lowest ID reachable from node 3. So if we assign all the low-length values to all the nodes, we get the following setup. From this view, you realize that all nodes which have the same low-length value belong to the same strongly connected component. If I assign colors to each SCC, you can clearly see that for each component, all the low-length values are the same. This seems a little too easy, right? Well, you're not wrong, there is a catch. The flaw with this technique is that it is highly dependent on the traversal order of the DFS, which is effectively random. Let me show you a counterexample. Suppose we take the same graph and rearrange the node IDs as though the DFS started at 0, went to node 1, got stuck in the component with node 1, continued on node 2, explored 3, got stuck again, and resumed at node 4, went to node 5, and finished at 6. You'll notice that this time, node 6 in the new graph has a low-length value of 0, which should indicate that node 6 is somehow part of node 0's strongly connected component, which we know is not the case. However, that's not the only issue. The real issue is that all the low-length values are the same, but there are clearly multiple strongly connected components in the graph. What's going on? Well, what's happening is that the low-length values are highly dependent on the order in which nodes are explored during the DFS, so we might not end up with the correct arrangement of node IDs for our low-length values to tell us which nodes are in which SCCs. This is where Tarzan's algorithm kicks in. Tarzan's maintains an invariant to prevent low-length values of multiple strongly connected components from interfering with each other. So to cope with the random traversal order of the depth first search, Tarzan's algorithm maintains a set, often as a stack, of valid nodes from which to update low-length values from. How the stack works is that nodes are added to the stack as nodes are explored for the first time, and nodes are removed from the stack each time a strongly connected component is found. Taking a step back, if the variables u and v are nodes in our graph, and we are currently exploring node u, then our new low-length update condition is that to update node u's low-length value to node v's low-length value, there has to be a path of edges from u to v, and node v must be on the stack. Another small difference we're going to make to finding the correct low-length values is that instead of finding all the low-length values after the fact, we're going to update them as we do our depth first search on the fly, if you will. This will allow us to obtain a linear time complexity. We'll be doing an example in the following slides, but this is Tarzan's algorithm in a nutshell. Start out and mark each node as unvisited. Start the depth first search somewhere and don't stop until all the nodes are visited. Upon visiting a node, assign it an ID and a low-length value. Additionally, also mark the node as visited and add it to the scene stack. On the depth first search callback after the recursion comes back, if the previous node is on the stack, then min the current node's low-length value with the last node's low-length value. This is essentially what will allow low-length values to propagate throughout cycles. After visiting all a node's neighbors, if the current node started the strongly connected component, then pop off all nodes from the stack which are in the strongly connected component. You know a node started a strongly connected component if its ID is equal to its low-length value. I'll let you think about that a bit more and it'll start making sense. Let's do an example. I'm going to mark unvisited nodes as blue, nodes for which the depth first search is still exploring some neighbors as orange, and nodes which the depth first search has explored all of its neighbors as gray. Note that if a node is orange or gray, then it is on the stack and we can update its low-length value. I will also be tracking the nodes which are on the stack in the left column, so keep your eyes peeled on that as well. So let's start our depth first search. So just randomly pick a node and start there. As we explore unvisited nodes, give each node an ID and a low-length value equal to the ID. So now we're at node 2 and our only option is to now visit node 0. Since node 0 is already visited, we don't want to visit it again, so now we backtrack. On the backtracking, since node 0 is on the stack, we take the minimum of the current node's low-length value and node 0's low-length value. Similarly, now min the low-length value of the node we were just at, which is node 1, with node 2. And also the same for node 0. Upon returning back to node 0, we realize that we've actually finished a strongly connected component since we visited all the neighbors of node 0 and its ID is equal to its low-length value. This means we need to remove all the nodes associated with the strongly connected component from the stack. However, we're not done exploring the graph, so pick another node at random. Let's start at node 3 and go right. Our only option is to go down. Now we're at node 5. Let's take the edge to node 0. So node 0 is already visited, so we can't go there. On the callback, we notice that node 0 is not on the stack at the moment, so we can't min node 5's low-length value against node 0. This is actually very, very good, because if we did, then we would contaminate the strongly connected component node 5 is part of with a lower low-length value, which node 0 has to offer. So let's go to node 6. So now we have 3 edges to choose from. Let's take the one on the right. Node 2 is not on the stack, so don't min with its low-length value. Now let's take the left edge to node 4. Node 4 is on the stack, so we can min its low-length value, giving node 6 also a low-length value of 4. The last edge we need to visit is the one going to node 0. This is a situation where node 0 is not on the stack, so we can't min with its low-length value. On the callback, node 5 can min with node 6's low-length value because it is on the stack. Similarly for node 4. Coming back to node 4, we visited all its neighbors and its ID is equal to its low-length value, so it marks the start of a strongly connected component. So we now have to remove all associated nodes in the strongly connected component from the stack. These would be all of the purple nodes. Now, coming back to node 3, we cannot min its low-length value with node 4 because we just removed node 4 from the stack. You will also notice that node 3's ID is equal to its low-length value, so it should be the start of a strongly connected component. However, we have not finished visiting all of node 3's neighbors, so we cannot make that assessment just yet. Now take the downward edge to visit node 7. Now take the edge to node 5. On the callback, notice that node 5 is not on the stack, so we don't min with its low-length value. Now up to node 3. On the callback, we can min with node 3's low-length since node 3 is on stack. Also min with node 7. So now we've finished with the last strongly connected component. All we need to do is remove all associated nodes from the stack. And that's how Tarzan's algorithm works to find strongly connected components. Very beautiful, isn't it? Let's look at some pseudocode for how this works. I think it will solidify your understanding. To get started, in the global or class scope, I define a few variables that we'll need. The first is a constant to represent unvisited nodes. Then comes n, the number of nodes in the graph, and g, an adjacency list of directed edges. Both n and g are inputs to this algorithm. Then comes two variables, id to give each node an id, and SCC count to track the number of strongly connected components found. After, I define a few arrays which store auxiliary information about the nodes in our graph. The first array is IDs, which stores the ID of each node, then is low to store the low-length values, and finally on stack to track whether or not a node is on the stack. Finally is the stack data structure itself, which should at minimum support push and pop operations. Inside the find SCCs method, the first thing I do is assign the ID of each node to be unvisited. The IDs array will be serving to track whether or not a node has been visited, as well as what a node's ID is. In the following loop, I iterate through all the nodes in the graph. There, I start a depth first search on node I if node I has not yet been visited. At the end, I return the array low and array of lowing values, which will be the final output of the algorithm. Now let's look at what's happening inside the depth first search method, which is really where all the magic happens. So this is the inside of the depth first search method. The input argument to the depth first search method is a variable called at, which I use to denote the ID of the node we are currently at. On the first three lines, I do some housekeeping stuff, which is add the current node to the stack, mark the current node as being on the stack, and give an ID and a lowing value to the current node. Then comes the part where I visit all the neighbors of the current node. To do this, I reach into a graph stored as an adjacency list and loop over a variable called to, which represents the ID of the node we're going to. And the next line says that if the node we're going to is unvisited, then visit it. Remember, the IDs array tracks the ID of node I, but also whether or not node I has been visited. This next line is very important. In fact, it's probably the most important line on the slide. The first thing to notice is that this line happens after the recursive call to the depth first search method, meaning that this line gets called on the callback from the depth first search. The line says that if the node we just came from is on stack, then min the current lowing value with the node we were just at. This is what allows the lowing values to propagate throughout a cycle. So after we finish the for loop that visited all the neighbors of the current node, we need to check if we're at the start of a strongly connected component. To check if we're at the start of a strongly connected component, check the ID of the current node is equal to the lowing value for that node. After we have identified that we're at the beginning of a completed strongly connected component, pop off all the nodes inside the strongly connected component from the stack. As we're popping nodes from the stack, also mark off nodes as no longer being on the stack. One more critical thing we need to do while we're removing nodes from our stack is make sure that all nodes which are part of the same strongly connected component have the same ID. So here I just assign each node have the same ID as the ID of the node which started the strongly connected component. Last things are to stop popping off nodes from the stack once we reach the start of the strongly connected component, and also increment the strongly connected component count if you want to track the number of strongly connected components that were found. Well, that's all I have for TarGen's strongly connected components algorithm. As always, there's working source code for this algorithm at github.com/williamfrieza/algorithms. The link should be in the description. And folks, thanks for watching. Drop a comment if you have any inquiries. Like this video and subscribe for more mathematics and computer science videos. Cheers.
Oh, I guess I understand. It starts here, and then for every node, it calls recursively, which creates the stack structure, which is the example that the explanation he was giving
You
here,
want to visit it.
of visiting all of the nodes, the neighbors, and adding the ID. Is gonna happen here. I kind of understand, but it's still really hard to understand what it means exactly to be a strongly connected component. Like it's a cycle inside of the graph, and then, like, I don't know. It's very confusing. And the reason why it tries here is because if it is the last node, then it's not gonna have any other nodes there, any other successors. And this is what creates the tree structure. So inside of here, like outside you have the graph, and then as you explore with depth first search, it creates the tree structure. And then through the tree structure, you create these rules to determine what kind of connection the nodes have. And then based on those connections, you check to see if it is a strongly connected component or not, based on whether it has a cycle inside. I think that's what's going on. So when it reaches the bottom, it's gonna be like this, so it's not gonna loop anymore. But if it's not the bottom, then it calls recursively and finds the minimum value, which is the ID thing that the guy was talking about. Just see if it's a successor or not. And then it pops from the recursion that it did there in the beginning. Because it's gonna be that tree structure. This transforms into a tree structure, where it stores the low link as the minimum value of the node and the successors. It's becoming more and more clear, but it's still gonna take some time. I think I'm gonna watch videos off stream again and research this off stream. Because the other ones I'm gonna have to watch a bunch of videos as well, so I was gonna stay more today, but I think it's not very good probably. Because I just have to watch a bunch of videos first, and then if I still don't understand, then I read articles about it. And it makes sense, but it's hard to understand when you think about, because you have to think about different graphs and where this wouldn't be the case, where two nodes are not connected. And obviously you can think about the graphs where you have some sort of cycle, or because it's a directed graph, the one node can reach the other one, but it's hard to understand. It's not really clear. So I guess one question that I have is if strongly you can only find strongly connected components on directed graphs. And so the tangents work for directed only. Yeah, that's what I was thinking. So I think a good way to put it is that strongly connected component is a cycle in a directed graph. Yeah, but he's saying that is a maximal strongly connected subgraph, which implies there is a difference, but he didn't talk about the difference. And this makes sense as well. And the challenging understanding is not even the thing, is more about the definitions, I think. Like what do they mean when they say something? That's the challenge. Yeah. So I think I get it now. And that's the thing that it wasn't clear before. So strongly connected is just for uh, directed graphs. And then it makes sense because in directed graphs you can have situations where some nodes are not reachable depending if you start from one node, they're not going to be reachable from that node because of the flow of the path. Because you can't go back because it's directed. But in undirected is whenever you have a cycle. Or when you have a graph that has different clusters of nodes that are separated and not connected necessarily, but they are part of the same graph for some reason. But then it depends on the definition because it depends on what do you mean by graph, because you can mean that a graph is only when you have edges connecting nodes. So if you have a case where you have two graphs that are not connected, then it would be two different graphs and not the same graph instead of just. So in that case, in that definition, it means that it's only when you have a cycle in the graph. Strongly connected. And this is the stuff that I wanna say, but I'm not really sure about it, which is that on undirected graphs it is a cycle. So I'm not really sure whether or not you put that there. I think I'm gonna leave it like this, and then this part I'm gonna leave it the way that it is. And I think writing it like this is gonna make it easier for people to understand, because that's the main problem I think I was having there in the beginning. And the other thing that I'm gonna talk about here is gonna be the whole relationship between the tree structure and the graph. That because you're using recursion, then it allows you to make rule sets based on a tree structure, because recursion creates a tree structure as you're traversing the graph. And that's gonna make it easier for people to understand as well. Strongly connected component exists on directed graphs, and it's when every node is reachable from every other node in a portion of that graph. So one example would be a cycle inside of a bigger graph, because you can get to any node of that cycle, and the cycle is a part of the bigger graph. It's considered to be a strongly connected component. In undirected graphs, it is connected when there is a path between two nodes, so it's not very common to use SCC. When it comes to the undirected graphs, it makes more sense to find them whenever you want to find connectivity between nodes in a directed graph. Yeah, I think this is good. Properties of strongly connected components. A strongly connected component is a maximal subgraph that is strongly connected. It is not possible to add any nodes to the subgraph without breaking the property of strong connectivity. Additionally, any two nodes in an SCC are connected by a directed path in both directions. It is important to note that a directed graph can have multiple SCCs. In fact, the set of all SCCs of a directed graph forms a partition of the node sets of the graph. This means that each node in the graph belongs to exactly one SCC. I think it's fine to leave it like this here, even if it's flagged as AI, because it makes sense. The only thing that I'm not really sure if it's redundant or not. But I think it is not redundant because it has this additional information here. So I think that this is probably good to leave it like this. Yeah, because it is explaining the maximal. Yeah, it's a maximal subgraph that is strongly connected. So it's only connected if it's not the maximal subgraph, because you can have the connectivity property inside of a strongly connected component, because it's just a subset of the strongly connected component. But then the strongly connected component is the maximum reach you can get for that cycle inside of the bigger graph. I think a different way to say is just a cycle, because if every node is reachable in the subgraph, it's going to be a cycle. So it's a lot more easier to understand if you say that is a cycle inside of the directed graph. But I might be missing something here, so because the definitions, and this is the stuff that I was talking about, where is the problem with definitions, because the definitions might be in something else, but when you intuitively think about a cycle, you can think about it as being something that connects all the nodes inside of the graph. But there might be a small difference in the definition. At this part, I think I understand is the concept of the ID that the guy from the video was talking about. Should always push such the stack, such in the node in the DFS order. Okay, so the low link is gonna be equivalent to the traversal on the on the tree structure of the DFS. And that's gonna be used to get the relationship between ancestors and the bridge, or I forgot the name that the guy gave. Like forward, then backward, and then the other one that I forgot. I think I understand. The question is, should I rewrite this or not? Because I think from someone's point of view that doesn't know anything about this, it may be confusing. So I'm thinking about what place I should add the stuff that I talked about, the tree structure, because I think that's going to make it easier for people to understand. That what you're doing on the specific algorithm is transform the graph into a tree by using recursion. And the reason why you do that is because you can find the properties of connectivity based on the IDs in the structure of the tree. And that's why you use that for search. And the IDs are gonna be, you're gonna keep track of the IDs, which are gonna be on the tree structure, and you're gonna use that to verify the strong connectivity. And then if it is, you pop out the nodes and put on the global array of strong connectivity, I think. Yeah, results. You put on the results the list that is going to contain the strongly connected ones. So the result is going to be a list of lists, and it's going to contain. So I think whether or not should I put here, I think I'm going to study this one as well. I think I'm probably going to change this thing here. Comographer, blah, blah, blah. I think here is going to be the point. I think the rest I'm gonna keep it there. Because I think it's fine. One column algorithm for finding the strongly connected components of a directed graph is Stargent's algorithm. This algorithm uses depth first search to identify the SCCs. The basic idea of the algorithm is to perform DFS on the graph, keeping track of the nodes that have been visited and the order in which they were visited. The algorithm starts by initializing a stack, a visited array, and a low link array. This stack, I'm gonna ask ChatGPT what this is. I think, like, based on the algorithm, I can understand based on this thing here, but I don't know the definition of it. Low link array. Like, it's understandable, but it would be better to have the definition and see if I can either explain what it is or put it like something else, change to something else. Because in there is gonna be a dictionary that is gonna keep track. It's gonna be the thing that keeps track of the IDs with the stack and something else there that I forgot. The stack in the index, I think. Yeah, index counter. Because the stack are the ones that are currently being visited and creating this recursion here. So the stack is going to be a tree structure, and the low link connects the stack with the index counter, which allows you to check for the strong connectivity based on this minimum value, which is going to be the value of the low link of the node, which is the ID. And then after it does all the recursion and creates the tree structure, then it's gonna check to see if the node is the root one, and then it's gonna traverse all the other ones for the connected. Because if it isn't the root, then it means that it's not a strongly connected component. I think that's, yeah, because it's a cycle, so the elements, or maybe not, maybe, yeah, let's see, index. Oh yeah, it's because here. Because you added to the index all the successors. So the last one is gonna be the node, because it's the starting one also. But maybe I'm confusing things here. But I think that's how it works. And if it isn't, then it's not gonna be strongly connected. But if it is, then because this means that it's a cycle, so it means that, yeah, it's pretty much a cycle in my eyes, which is the same as saying that every node is reachable from every other node, because it is a cycle in a directed graph. So this confirms after the recursion of the tree, because you're traversing the nodes in this part here based on the minimum value. And then if the last one is equal to the one in the beginning, it is a strongly connected component. But I'm not 100% sure about this. And because it's checking the value, so if the value is the same, then and that's when it's going back here, I think. So it reached the bottom and then it's going back. Maybe. But maybe not. Let me go back here. Focus on this thing first, and then I think I'm gonna use ChatGPT there to investigate parts of the code more in depth to make sure I understanding correctly, because recursion is really hard for me to understand. The algorithm starts by initializing a stack. Obviously, the stack is used to keep track of the nodes that are currently being visited, while the visited arrays is used to keep track of which nodes have been visited. The low link array is used to keep track of the lowest node that can be reached from a given node. And the lowest node that can be reached from a given node. The reason why the algorithm uses DFS is because whenever you use recursion, you transform the graph into a tree structure. Because recursion creates a tree structure of stacks, then you can utilize this property to verify the connections of nodes by making their ID to be linked with their position on the stack. Then based on their IDs, you determine whether or not the nodes visited create a strongly connected component. During their DFS, you should know this pushed on to the stack, and its low link value is set to the index of the node in the DFS order. As the algorithm explores each node's neighbors, it updates the low link values of the neighboring nodes if necessary. Maybe this is better to put after this thing here. Yeah, I think it makes more sense, because after explaining the DFS parts makes more sense too. Explain why it uses the DFS. Which is this low link thing here, I think. Fuck. There's this line here that I'm trying to explain. Yeah, it's checking because it updates the low link on the recursion, I think. And the index of the node is always the is established here or outside. No, established here. So the index doesn't change, I think, since the beginning of the algorithm. I'm gonna have to study more to understand, I think. Pretty sure I understand now the way it works, but not the nuances here. It's increasing the index counter. So the index counter is the levels of the tree, I think. So it's gonna break when it's I think I'm gonna finish this off stream when I use ChatGPT to understand more this algorithm here, the parts of the algorithm. I think I understand the concepts now already, and I might modify some things here. But I think I'm gonna leave it like this part here. And then this I'm gonna see if it makes sense or not. Yeah, I might change this if I realize, or if I think about I'm not sure how to say this, but if after exploring this thing here with ChatGPT, I realize that the way that I'm thinking is wrong, which I don't think it is. I think that is correct, but the way that I'm thinking about it. But if for whatever reason it's different than I thought, then I think I'm gonna change this part here. But if not, I'm gonna leave it like this, I think. I'm gonna study this offstring. I might come back today to continue doing this, but I'm not really sure. I think I'll be happy if I finish. I think they're strongly connected. I'm gonna finish today for sure. But then I would like to finish either all of them or just one more of this shoe. But for figuring out this shoe, I think I'm gonna start with this one because I think it's harder than this one. This one I already studied a little bit, but I think this one's gonna be hard as well. And the problem with this shoe is that I have to watch a bunch of videos before to understand the framing of the thing. It's gonna be, they're both difficult, I think. So it might take me one day for each to figure out. So I'm gonna think about upstream whether or not I'm gonna come back, depending on how long it takes to finish this one, and to watch videos about this one. So if not, I'm probably gonna come back tomorrow to continue doing this, and if I finish this off stream, then I'm gonna continue with the data structure articles.